Good morning or afternoon. My name is Fedi Khalfawi and today I'll present quantized side tuning, a method proposed by researchers from CMU and Tsinghua University. This approach enables efficient fine-tuning of large language models on commodity GPUs. Fine-tuning LLMs explodes memory along three axes: weights, optimizer states, and activations. Prior work like QLoRa compresses weights using 4-bit quantization, but leaves activations untouched. As a result, practitioners must checkpoint and use very small batch sizes. Traditional PFT methods, such as LoRa, reduce the number of trainable parameters, yet still catches about 70% of activations. In this paper, the authors set out to design a single approach that reduces all three memory sources without sacrificing accuracy. Before we dive into the detailed technical blocks, here is a high-level view of what the authors are proposing with quantized side tuning. First, they show for the first time that it's possible to quantize a frozen backbone to 4 bits, attach a small side network, and still match full fine-tuning performance. Second, they successfully reduce all three major memory sources at once: weights, optimizer states, and activations, something that previous methods like LoRa and QLoRa could not fully achieve. Finally, the architecture remains extremely clean and efficient. The side network handles both forward and backward passes, while the frozen backbone only participates in the forward pass. In the next slides, I'll go deeper into how each of these ideas is implemented. The first stage of their method is a 4-bit quantization of the backbone. They use a blockwise uniform quantization method called NF4 or FP4. Each small block of 16-bit weights is rescaled by its absolute maximum, and then rounded into 4 bits as shown in equation 1. During the forward pass, the model applies dequantization on the fly, as shown in equation 3, to reconstruct approximate 16-bit activations. This compression reduces weight memory by about 4 times compared to FP16, while keeping computations efficient and friendly for standard GPUs. As you can see in the diagram, the frozen backbone is fully quantized before the side network is fully attached in stage 2. The second stage is side tuning. For each transformer layer, they mix two sources: the downsampled frozen activation from the backbone and the previous side network activation. The mixing weight beta is a learnable scalar, derived by applying a sigma to gamma as shown in the equation. First, the hidden state from the backbone is downsampled by a factor of approximately 16, using lightweight adapter, LoRa, or pooling model. After passing through a small side layer, the hidden state is upsampled back to match the original dimensions before reaching the LM head. Only the gating scalars gamma and the weights of the down and up projections are trainable. The 4-bit backbone remains completely frozen, with no gradients flowing through it. As you can see in the diagram, the green path represents the side network where gradients propagate, while the frozen blue backbone is only used for forward computations. Now that the overall architecture is clear, this figure zooms into one transformer block. After each frozen backbone, the hidden state is passed through a downsampler, compressing the width by a factor of r. The compressed state flows through a small side layer, and at the output it's blended with the downsampled frozen backbone, using the learnable scalar beta. This gated combination then flows forward toward the next layer. It is important to observe that the frozen backbone outputs are used only for forward computation, while all gradient flow is confined to the green side network. This table highlights why quantized side tuning achieves such a dramatic memory reduction compared to full fine-tuning and QLoRa. First, weights are compressed from 16-bit to 4-bit, just like QLoRa. Second, optimizer states are only maintained for the small side network, whereas in the full fine-tuning, optimizers store 3 copies of the full parameter set. Third, and most importantly, intermediate activations are not cached for the frozen backbone. Instead, only the side network activations are saved, which reduces activation memory down to about 30%. As a result, for a Llama 2 70 billion model with batch 16 and sequence length 384, the total GPU memory footprint drops from 197 to just 56 gigabytes, making QST about 2.3 times lighter than QLoRa and 7 times lighter than full fine-tuning. With the method established, we now look at empirical results to assess how well quantized site tuning performs compared to baselines like QLOR. On the glue benchmark, quantized site tuning maintains strong performance while drastically reducing memory and trainable parameters across multiple OOPT models. QST stays within 1.3 percentage points of QLoRa while using half the memory or less. For instance, on OOPT 6.7 billion, QST achieves an average score of 84.2, while QLoRa's average was 85.5. Importantly, QST only fine-tunes about 0.4 of parameters compared to 2 to 4% for methods like LoRa or LST. So overall, QST achieves competitive accuracy with significantly lower memory and compute power. Here are the results on the MMLU5 short benchmark across both OOPT models and Llama 2 models. On average, QST matches or slightly outperforms QLoR with a 0.1 percentage point gain overall. For example, if you look at the Llama 270 billion model, QST reaches 63.9 accuracy versus 64.1 for QLoR, virtually the same. But in terms of memory, QST dramatically reduces the footprint for Llama 270 billion model. It cuts memory usage from 95.5 GB down to 56 GB. Across all models, the author reports an average 1.8 times memory reduction. Now we move to the author's ablation studies to better understand their design choices. The first ablation focuses on the reduction factor R, which controls how much the hidden states are compressed. They sweep R from 2 to 64 on Llama 2 models, 7 billion, 13 billion, and 70 billion. As shown in the left plot, accuracy remains stable until it reaches R equals 16, after which it starts to decline. Meanwhile, in the middle and the right plots, memory footprint and flops per token drop sharply up to R equals 16. Based on this, the authors select R equals 16 as the best trade-off between performance and efficiency. Next, the authors study the choice of downsampler model used after the frozen backbone. In this appellation, they compare different downsampling options: linear, LoRa, adapter, max pooling, and average pooling. Adapters give the best accuracy at 45.1%, while keeping parameters overhead low. Pooling methods like max pooling and average pooling incur no extra parameters, but lose about 2 percentage points of accuracy. Based on this trade-off, the authors select adapters as the default downsampler. The third ablation studies the effect of the compute data type during training. They find that QST remains stable whether using BF16 or FP16. In contrast, QLoRa struggles when trained in FP16 with significant drops in accuracy. For example, on the MRPC task, QLoRa drops to 68%, while QST maintains 85.6%. This shows that QST is more robust and does not require BF16 only hardware to work well. The final evaluation measures chatbot generation quality on empty bench using the Llama 270 billion backbone. Three versions are compared: Vanilla in orange, QLoRa in cyan, and QST in gold. As you can see in the radar plot, QST leads in 4 out of 8 categories, especially in STEM, extraction, coding, and roleplay. It matches the baseline in humanities and stays competitive in reasoning and math. In terms of overall score, QST achieves 7.07, higher than both Vanilla at 6.8 and QLoRa at 6.6. The key message is that the lightweight side network does not degrade generation quality, it can even improve it. To finish, here are some limitations and future ideas I noticed. First, the side network adds a small latency overhead during inference. Second, the reduction factor R is fixed. Using an adaptive width could help. And third, applying activation quantization inside the side network could save even more memory. Overall, the method is efficient but still has room for future improvement. To summarize, the key takeaways are: first, quantized side tuning combines 4-bit quantization with a lightweight side network. Second, it reduces memory on weights, activations, and optimizer states all at once. Third, it achieves comparable or better accuracy than QLoRa with up to 2 to 3 times speed up. Finally, it offers a practical way to fine-tune 70 billion scale models on commodity GPUs, which was previously very challenging.